Let us now examine the steady-state assumption. The derivation of the kinetic equation using the steady-state assumption is similar to that using the rapid equilibrium assumption, with a key exception. After the Michaelis-Menten equation, a slightly improved equation derived using the steady-state assumption was published about 12 years later by Briggs and Haldane in 1925. Because a similar strategy will be used, it is recommended that you first review the previously discussed rapid equilibrium assumption that I have posted on YouTube. Let's look at a one-substrate, one-product kinetic mechanism. In this mechanism, the enzyme first binds to the substrate to form the ES complex at a rate of K1. Once formed, the ES complex either dissociates back into E and S at a rate of K-1 or is transformed forward by the enzyme in a product at a rate of K2. K2, the catalytic step in which chemical transformation of the substrate occurs, is also referred to as Kcat. Note that in this mechanism, no EP complex is shown. This means that, once formed, the product dissociates rapidly from the enzyme to form E plus P. In other words, the half-life of the EP complex approaches zero. If the product dissociates slowly from the enzyme, then the EP complex must be included in this mechanism. Similar to the Michaelis-Menten approach, K2, the chemical step, is assumed to take place much more slowly than K1 and K-1. Therefore, K2 is the rate-limiting step. Based on the bottleneck assumption, the overall rate of the reaction is determined by the slowest step. Thus, the reaction velocity is equal to Kcat multiplied by the concentration of the ES complex. Next, write the equation for the total amount of enzyme presence in the reaction mixture. According to the law of mass action, the total enzyme concentration in the reaction mixture is equal to the sum of the free enzyme concentration and the concentration of the ES complex, as shown. Because the velocity depends on the amount of enzyme present in the reaction mixture, increasing the total amount of enzyme increases the reaction rate accordingly. Therefore, one must take this into account by dividing the reaction velocity by the total amount of enzyme present in the reaction mixture. This equation would be perfectly adequate if the concentration of the ES complex were known. However, because the concentration of the ES complex formed in the reaction is unknown and cannot be measured directly, Briggs and Haldane used the steady-state assumption to express this unknown concentration in terms of known parameters. When an enzyme and substrate are added to a reaction mixture, the concentration of the ES complex slowly increases with time. However, after a certain period, the concentration of the ES complex reaches a steady level. At the steady state, the rate of ES complex formation is equal to the rate of its breakdown. When this happens, dES divided by dt is constant over time and is equal to zero. The only way the ES complex can be formed is through collisions between free enzyme and substrate at a rate of K1. However, there are two pathways by which the ES complex disappears. The ES complex either dissociates backward into E and S or is transformed forward in a product, and the equation can be written as shown. At steady state, the rate of ES formation is equal to the rate of its breakdown, and the following equation can be written. This equation can then be rearranged by moving K-1 plus Kcat from the left-hand side of the equation to the right-hand side. The ES complex is now expressed in terms of the known concentrations of E and S and the rate constants, which will be determined from the plot. Next, substitute this expression into the velocity equation we previously derived. Simplify the equation by canceling out all terms that contain free enzyme E on the right-hand side of the equation. Move ET from the left-hand side of the equation to the right-hand side. By definition, the maximum velocity, or Vmax, depends solely on the total enzyme present in the reaction and its catalytic rate constant, Kcat. In other words, Vmax is equal to ET times Kcat. Now, multiply the numerator and denominator of the right-hand side of equation by the sum of K1 and Kcat divided by K1. When compared to the equation derived by Michaelis and Mentan, the two equations are similar, with the exception of this term. Now, if Km is defined as the sum of Kcat and K minus 1 divided by K1, and this definition is substituted into the above expression, the following equation is obtained. Thus, the same equation is obtained using either the steady state or rapid equilibrium assumption. However, the two differ in their definition of Km. Under the steady state assumption, Km is defined as the sum of Kcat and K minus 1 divided by K1, whereas the rapid equilibrium assumption defines Km as K minus 1 divided by K1. The catalytic step, Kcat, is assumed to be very small and therefore ignored, allowing the rapid equilibrium assumption to be made. Now, one may ask which equation is correct. The answer depends on the catalytic activity, or catalytic efficiency, of the enzyme in question. If the enzyme in question is highly catalytically active and has a large Kcat value, then Kcat cannot be assumed to be very small and ignored. An example of such an enzyme is triose phosphate isomerase. This enzyme has been shown to be nearly perfect and is a diffusion-controlled enzyme. In other words, this enzyme is so efficient that the overall rate of the reaction depends on how fast E and S collide to form ES complex. In the biotechnology industry, one of the goals of enzymologists is to improve the catalytic efficiency of an enzyme through genetic engineering for practical applications. Thus, when dealing with a highly catalytically efficient enzyme, the steady state assumption is more appropriate, and Km is equal to the sum of Kcat and K minus 1 divided by K1. Most enzymes encountered, on the other hand, are less catalytically active. If an enzyme is catalytically slow, then Kcat can be assumed to be small and ignored. In this case, the rapid equilibrium assumption can be made, and Km is equal to K minus 1 divided by K1. The Km determined from the plot is the true dissociation constant, or Kd, of the substrate from the active site of the enzyme.
ขณะนี้คุณกำลังฟัง JFE Club Radio